Hello everyone, in this video I will present my study, the enhanced teleoperation of construction robots using a generative adversarial network-based physiological signal augmentation framework. So in this presentation, first I will introduce the background of the study. The construction industry plays an important role in the US economy. However, in recent years, it suffers from several challenges, including the low productivity, the labor shortage, aging workforce, and the workers' high mental stress. So to solve these ever-existing challenges in the construction industry, the construction companies and the research communities have introduced robotics to the construction site. They expected to use these powerful machines to help workers to perform repetitive, physical demanding and dangerous tasks such as the bricklaying and the welding construction tasks. To implement these construction robots to the dynamic and unstructured sites, worker supervision and assistance are needed. And this is because due to the lack of human-like decision-making ability, these purely mechanical machines, robots, cannot deal with the task in the dynamic surroundings and the task with multifaceted design considerations. While correspondingly, the human-robot collaboration solution can systematically combine the technical advantages of robots, like the precisions and the repeatabilities, with workers' advantages, such as the flexibility, awareness, and decision-making abilities, so that the task that requires workers' decisions can be performed by the robots efficiently. However, when involving workers into the robot's working envelope, it may trigger new safety challenges to the construction site. More specifically, when workers and robots collaborate in the shared workplace, the lack of information exchange of their physical positions may trigger the collision accidents between workers and robots. And also, during the human-robot collaboration, the lack of information exchange of workers' mental states may make robots to keep imposing the excessive stress and cognitive load on workers due to the imbalanced working capability between the two, so that triggering the mental health problems of workers. Therefore, to achieve the safe human-robot collaboration environments, it is necessary to establish an effective communication channel between robots and their co-workers. To achieve such communication, workers' physiological signals, EEG signal, can be a feasible middleware. And this is because the EEG signal can reflect various information about human, like their intentions, mental stress, and cognitive load. So if we can decode this information from their EEG signals into digital information perceivable by robots, the robots can adjust their performance, such as the walking speed, the trajectory and the planned path in accordance with the information about workers, so that the communication between the workers and robots can be achieved. And this slide shows several representative studies of the established EEG-based communication pathway between robots and workers. Once the pathway is established, as shown in research 1, the robots can adjust its walking speed according to the worker's cognitive load decoded by EEG signals. And also in the second research, the robots can be controlled to change its trajectory as per worker's special EEG features. And likewise, in research 3, the robots can be controlled to correct their actions based on the worker's emotion measured by EEG signals. Okay. So according to the introduced background, next I will explain the problem statement and the research objective of the study. So once the EEG-driven communication pathway is established, to ensure its efficiency and reliability, one primary step is to obtain the high-quality EEG signal from the human brain. However, due to the small number of electrons, the EEG devices in the construction industry cannot collect high-quality EEG signals with enough spatial resolution, as compared in the following two groups of images, compared with the devices in the clinical domain that has 256 channels. The 32-channel EEG devices in construction site cannot cover the electrical field of brain comprehensively. And this deficiency will distort the collect EEG patterns, so that streaming the erroneous information from workers to robots and diminishing the reliability and accuracy of the established communication between robots and workers. Even worse, in the current construction industry, there is a lack of method to enhance the spatial resolution of captured EEG signals in EEG-driven human-robot communication. So this study, to bridge the gap, will develop and examine a generative adversarial network-based signal augmentation framework to produce high-quality EEG signal with improved spatial resolution. Okay, next I will explain the proposed framework to achieve such objective. Okay. As introduced, this study will employ the generative adversarial network, GEN, to propose the signal augmentation framework. GEN is the technique developed to empower the deep neural network to produce high-quality artificial images, audio, and biosignal data sets. And in this study, the proposed GEN-based framework has two components: the artificial EEG signal generation component, in which a GEN network will be trained to generate artificial EEG signal from the actual signals by using two deep networks, the discriminator network and the generator network. And the second component, the signal quality examination component, where the quality of generated artificial EEG signals will be examined by employing two widely accepted metrics. And if the artificial signals can pass both examinations, they will be regarded as the high quality artificial EEG signal and used to improve the spatial resolution of actual EEG signal. Otherwise, the generated artificial signal will be removed. And the next slides, I will provide more details about architecture of the two network, the discriminator and generator network. So as shown in this slides, the architecture of the generator has 3 upsampling blocks, and in each block, the bench normalization and the leaky relu activation functions will be employed to the convolutional layer. And conversely, the architecture of the discriminator has 3 downsampling blocks consisting of the convolutional layer, the bench normalization, and the leaky relu activation functions. And the reason of designing the architecture like this is because, as demonstrated by several studies, the upsampling and downsampling architectures of the GEN network can enhance the quality of generating artificial EEG signal. Okay, next, based on the proposed framework, I will explain the experiment designed to test the feasibility of the framework and the corresponding results. So in this study, we will use the EEG signal collected from the robot teleoperation experiment. To collect this dataset, 4 subjects will be asked to perform the motor imagery experiment. As shown in the experiment, subjects will be instructed to sit in front of the computer and to perform 2 sessions. First, 60 rounds motor imagery task of imaging the right hand movements by staring at the right arrow in the monitor. Second, the 60 rounds of motor imagery task by imagining the movements of the left hand by looking in the monitor and blinking left arrow. And after obtaining the dataset, the dataset will be entered into the proposed GEN-based framework to test the signal augmentation performance. Then the augmented dataset will be applied to the robot teleoperation tasks to test if the enhanced spatial resolution of EEG signal can improve the accuracy of decoding EEG signals into the robot control commands. And in this step, the ensemble machine learning classifier will be employed to decode EEG signals into left and right control commands. The right commands will control robots to move right, and the left command will control robots to move left. And this slide shows the final results of the experiment. As shown, by using the proposed framework, the proposed GEN-based framework, the spatial resolution of EEG signals can be improved by 40%. Then, by using the enhanced spatial resolution of the EEG signal, the robot teleoperation accuracy can be improved by 5%. Okay, and according to the results, next I will give the conclusion of this study. So the results of this study confirm the feasibility of the proposed GEN-based framework in increasing the spatial resolution of EEG signal by about 40%. And also the enhanced spatial resolution of EEG signals can further improve the accuracy and the reliability of interpretation of human EEG signals. As such, the study can be served as a basis for studies to establish the reliable, accurate communication between humans and the robots in the construction. And finally, I would like to thank the team members of RISLab for their support and help in this research. And thank you for watching this video.